Okay, well, I have to recap a little bit about what I spoke about at the beginning of this meeting, because this is, in a certain sense, the second half of that talk. I'd made the point using arguments like from Gödel's theorem and an argument from Goodstein's theorem, that the quality of understanding is not something computational, so you couldn't put it on a computer. I want to say a little bit more about things which are non-computable in mathematics. It's a very well-defined notion, but the argument that I was making is that consciousness, there are lots of things about consciousness, of course, apart from understanding, but the only thing that I can really make a statement about is the quality of understanding, because that quality, I argue, can be shown to be something non-computational. So let me go to the next slide just to show you an example of this sort of thing, which may give you the idea. If you want to consider tiling the Euclidean plane with shapes, here's an example which uses squares, regular hexagons, and regular dodecagons. That's 12-sided figures. And you can, from this picture, you can see that it's a periodic tiling. You can tile the entire plane with those three shapes in this way. Now, suppose we put some marks on these slides, on these shapes, and I've indicated them here. And the argument is that each one of those, you have to rotate it round until the marks match those of the next. So the dodecagon on the left here, the lines there, and the colors, the order in which the colors appear, have to match with the next thing sitting next to it, either a square or a hexagon. And the question is, how do you do this? Or how do you know that it tiles the plane altogether? I should say it does not tile it in any way which repeats itself. You might have an algorithm which says, okay, put enough tiles down in all possible ways until you get one which repeats itself, like in the previous picture where you have a repetitive design like this, which simply repeats itself forever. But in this example, that doesn't work. But let me give you some sort of idea about how you would see that it does tile a plane. It's not a universal way, but let me just indicate. Here I have what the tiling looks like, just the marks indicated, all in black rather than the two colors that I had before. And you can see sort of on the middle of the left-hand side, you can see a sort of ring there. And you can see shapes next to it. And in a way, it looks a bit like the thing we started with. In fact, that's how you could show that it does tile a plane. Because of this, when you get enough of them together, you begin to see that it makes shapes like the ones you had before. And that's how the tiling works. I'm not going to say anything more about it, really, but just to show the sort of way in which your understanding can be used even though it isn't following an algorithm. So this is a way you would see how those tiles will tile the entire plane. I'm not going into the details of that, but you can see from the general nature of this picture how you could repeat this and repeat this at different sort of sizes of hierarchy, and you could therefore cover the whole plane. I want to mention this just as a current interest, because this subject is of current interest. Only very recently, a man called David Smith produced this shape that you can see, something's called the hat, and you see the shaded one in the sort of middle, slightly to the bottom left, right. And it's the same shape, sometimes turned over, mostly one way up. And it's very remarkable that this shape will only tile the plane in a way which never repeats itself, and in a way is even more subtle than the one that I showed you before. So you have to, this is sort of indicating how the level of sophistication, you may have an algorithm that works at a certain level, but it's never going to encapsulate one's entire understanding of how these things work. I don't want to go into that anymore because that was really the subject of my previous talk, but I thought I'd lead you into that a little bit. Okay, and the question then was, okay, if there is something non-algorithmic in how human brains work, and I would say conscious brains are not just humans in my view, how conscious brains work, and how could that be part of the laws of physics? Because the laws of physics you could, in effect, put on a computer. There's a bit of a problem because you have to use the continuum rather than approximations to it. I don't regard that as the actual resolution of the issue. It seems to me that you can well enough model the continuum so that even though things like Newtonian mechanics even do depend on the continuum, you can approximate it by discrete calculations, and it's pretty well calculational. So Newtonian mechanics you could put on a computer. Maxwell's electrodynamics, a little bit more tricky, but you can put that on a computer too. Einstein's general relativity, more tricky still, but we have good evidence that it can be effectively put on a computer. The LIGO detector of gravitational waves detects signals which have been computed to indicate the inspiraling of black holes and so on. And so there are very, very powerful, precise calculations using general relativity, in general relativity to using computational techniques. So that it doesn't seem to be anything non-computational there again. What about the Schrödinger equation for the evolution of the quantum state? Again, there is something, a very deterministic and evolutionary computational equation with this, again, slight issue about being able to approximate the continuum with discrete calculations, but that doesn't seem to be the issue. But how about, just sort of by the process of elimination, the collapse of the wave function, which is something quite different. I should say also that this session is to do with determinism, or is that sort of issue. And the thing is, the collapse of the wave function, as we understand it, is not deterministic, but it's probabilistic. And just to say what it is, in quantum mechanics, you have this principle of superposition. You have two states, A and B are quantum states, might be states describing the world, and alpha and beta are complex numbers, ordinary real numbers, but with the addition of the square root of -1, if you don't know what complex numbers are. They're basic to quantum mechanics. You have to put them, those strange-looking numbers, but they're very clearly what the rules are about them and everything like that. So these complex numbers they're not the problem. You can certainly put them on a computer just as well as you could put a real number. Again, by approximations, but that seems to be good enough. Now, what about the collapse of the wave function? Now, the Schrödinger equation preserves these superpositions, and I've got this in this picture here. Suppose A and B are two states, and A evolves by the Schrödinger equation A prime, and B evolves to B prime. Then the combination alpha A plus beta B, that's using the one I had in the previous slide, will evolve to alpha A prime plus beta B prime. So the alpha and betas remain the same. The amplitudes, as they're called, the complex amplitudes, which represent how much of one state and how much of the other state is involved in this superposition, that remains constant, but A and B evolve according to the Schrödinger equation. But the collapse of the wave function is quite different. That happens when you make an observation on the system. It's a bit obscure what that really means. But if you make an observation on the system, then suddenly the things behave very differently. You take alpha and beta, you take their squared modulus, that means the square of the distance from the origin in the complex plane, where you represent the alpha and beta in this plane, and the ratio of those two squared moduli gives you the ratio of the probabilities of A and being the result, A or B being the result. So your measurement is supposed to decide whether your state is A or B, even though it's this superposition, and this superposition then tells you it's that probability mixture of A and B. It becomes a probability mixture, it becomes an indeterminate procedure, and that's the way standard quantum mechanics is argued to work. And these things are meant to be just probabilities. It doesn't say anything more than that. So you have this, well, there seems to be a role for free will, sometimes people say, because, well, the thing is not deterministic. I mean, there was the famous point of view introduced by Laplace after Newton had put forward his laws, and it seemed clear that if you knew what the complete state of the world was at any time, then the Newtonian equations would tell you what the state was the next 10 minutes or as long as you like. And that evolution would therefore be inbuilt in what the system was. There is no role, it seems, for free will. Do we have a role for free will here? Well, not as it stands, because it's meant to be just probabilities. So there has to be more than that if you're going to find a role for free will. But at least it does open the door for a possible role for free will, whatever that means. Let me continue. I should also mention, which I think I mentioned in the last talk I gave, is that the collapse of the wave function, in my view, is not due to the conscious observer looking at the state. So there were people like von Neumann and Wigner who took the view that it was the conscious being, the external conscious experimenter, looking at the alternatives that your experiment seems to produce, and it's the observer looking at the system which produces the state. I'm not taking that view at all. I'm taking the view that it has nothing to do with the conscious observer observing it. It's really the other way around, that whatever consciousness is somehow takes advantage of what the collapse of the wave function is. Now, in this slide, I'm indicating the point of view introduced originally by Dioschi. A couple of years later, I independently thought of it using a different type of argument from his, which I outlined in my previous talk. And it tells you, if you have a superposition between two bodies, or at least a body and itself in a different location, say, the body over here and the body over there, and it's a superposition between those two states, then that state doesn't remain in that superposition forever, but there is a lifetime. If it's very, very tiny, then the lifetime will be very, very long. If it's large, then the lifetime will be short. And the formula comes about from this quantity Eg. Eg is the gravitational self-energy of the difference between the two states. I want to say a little bit more about that Eg. Here I have a little calculation one can do. Here I'm imagining you've got a uniform sphere, and this uniform sphere is put into a superposition of being in one location and another. So at the top you can see the sphere in one location, and the dotted one is the sphere in the other location, and that would be a quantum state, that it could be in that state. Now, what is Eg? You can do a little calculation of what Eg is, and I have a graph of it at the bottom. When they're complete, the two are completely on top of each other, with an Eg is 0, as you start to pull them apart, then you see this curve right at the bottom of this picture goes up as you move them apart until the dotted line there is when they're in contact, and then it still goes up as you move them apart, but not by so much. So that gives you a picture of what Eg looks like for a sphere moving apart like this. Okay, well, now, here I have a space-time picture of that. I'm imagining time is going up, and the sphere is represented by this vertical line right at the bottom. So it's in one place. And then as time progresses, going up the picture, time you can think of as represented by horizontal slices of this picture as they go up, then you start to separate them apart, and after a certain time, this time h cross over Eg, that h cross is Dirac's form of the Planck's constant, and that tells you the order of time which it would take for it to collapse. And so I'm supposing that where these dotted lines cease and one of these things becomes the world line of the actual particle, so it's right at the top you see that the body has gone into the superposition of 2, and then the collapse takes place, and it becomes the left-hand one in this picture. It might have been the right-hand one, but it was the left-handed one in this case. Now, there's something a little puzzling about this picture when you consider relativity, because in relativity, there isn't just a time which plods along and is represented by the horizontal slices moving up in this picture, but depending upon the sort of state of an observer, sort of an impartial observer moving along, looking at the whole thing, if the observer is moving from left to right, then you would take the T slices, which tilted upwards to the right. If the observer is moving from right to left, then according to that observer, the time slices would be tilted in the other direction. Now you have a bit of a problem here, because if the body has disappeared, you see the dotted lines of the world line now become a superposition of those two possibilities, and you have the point Q and the point Q star. And what I'm saying is that what it collapses to Q star. Now, in the reference frame that I started with the horizontal lines representing the progression of time, then as soon as one has disappeared, the whole state becomes the other. But now, according to these moving observers, that doesn't work. The T observer, which is moving to the right, it's as though the one has disappeared before the state has become entirely the other one. So that as far as that observer is concerned, there's still a chance that the other one might disappear too, and the whole thing might disappear. That's ridiculous. It doesn't make any sense. And you might consider another observer moving the other way, and then the whole state has become Q star, when there's still a possibility that it might be Q. So it doesn't make any sense. The picture just doesn't work for the other observers. So how do you make the picture work? Well, the only way I can see, I would say there is one bit of a possibility too, which I have to consider, but I'm going to say the only way that really makes sense is that the collapse goes right back to the original point, and that when the collapse has happened, in a certain sense of when, it actually goes back retroactively to the point O. So when the collapse decides that it's going to be the left-hand branch, the Q star thing, it's as though the reality goes back to O. This is actually what I'm calling classical reality. In order to make sense of all these ideas, you really have to have two kinds of reality. You have to have the classical reality, which sort of goes back to the origin point, or it goes to the the other one disappears in this view. So it goes back to the origin point, and the decision, in a certain sense, of which it is, has to be made at that point where they start to separate, which is a bit of a strange picture. There is a sort of loophole to this, which I did think about. Philip Pearl and various people consider a thing that they call gambler's ruin, and you have an amplitude which sort of wiggles around attached to these two dotted things in the middle of the picture, and when one of them gets so much bigger than the other that you say, well, you more or less consider that it's happened, that it's what they call gambler's ruin, that they're gambling against each other, and then one of them has so much money that the other one might as well give up. It's not terribly clear when the give-up takes place, and that's the problem I still have with it. But nevertheless, it takes it to a different level, and you might consider that the amplitudes are wiggling around independently, and then one gets too small, then the other one becomes the real state. I don't think it really resolves this issue, and I'm pretty sure it doesn't from various other arguments which I can't really give you here. But there is a problem that if you don't take the collapse to be at the initial point where they start to separate, you have a bit of a problem for saying when the reality takes place. Now, I'm taking the view that this is classical reality. Classical reality is the robust form of reality, and it has this characteristic feature that I can ask the state, I can say, hello state, what is your state of reality? And it comes back to me, and I says, oh, my state is I can have a body like this object here, and I can ask it what its shape is, and it says I've got a round thing at the end and a round thing in the middle, and more or less cylindrical and things like that. Now, quantum reality, you can't do that. What you can do is you have an idea what the state is, a pretty good idea, and you can say, is your state X? You think it should be X by now, and you ask it whether it's X. And if you've got it right, then it will say, yes, you got it right with certainty. This is what I'm calling Einstein's dictum. He introduced this idea of what I'm calling quantum reality. And you can see what I'm saying here. It's more or less what I was saying there. That if you can ask the system with certainty and without disturbing the state, so if you know what the state ought to evolve to, then you can say, is your state, as I think it ought to be by now, evolving the Schrödinger equation? And the thing will say, yes, you got it right, with certainty. And that gives it a kind of reality. However, it is a different kind of reality. And the key thing to this is that it is a different kind of reality. Let me give you an example of quantum reality. This is a very simple example. This is a spin-half particle And the notion of spin for a spin half particle is very beautiful in quantum mechanics, because you could think of it as behaving like a little sphere spinning around an axis. The amount of the spin is always the same, but the direction of the spin about that axis could be different. You've got all these different possible states. Now, I'm supposing the state is, as indicated in this picture, up and to the right a bit. Then that is a linear combination, a quantum combination of up and down. So you might usually talk about up and down as the two basic states. Up and down means right-handed about the upward direction or right-handed about the downward direction. And then any other state is this quantum complex combination. Well, I've got W and Z instead of alpha and beta, but that's the same thing. W times up plus Z times down will produce all the possible different directions. And I always regard this extremely beautiful because it ties in these complex amplitude of quantum mechanics, which seem very abstract things, with something very concrete, namely this direction in space. And the direction in space is tied up with this quantum notion of superposition of these different directions of possible spin, and it ties it up with the directions in space, which I always regard as an extremely elegant and beautiful feature of quantum mechanics. Now, you see, here is an example of quantum reality, because if you've done some experiments and it's put it into the state pointing in the direction we have in the picture, up and to the right, then you can make a measurement on it in that direction, and it says, yes, you got it right with certainty. I can do it 100 times. Every single time it says, yes, you got it right. If I tried up or down, then it would say sometimes yes, sometimes no. These probabilities being given by the squared modulus of the W and the Z, and the ratio of the two, which will give you the probability. So when you don't get probability, that means you got it right. When you haven't got it quite right, you'll get probabilities. And if it's almost right, you'll get almost certainty for your probabilities. So that's where it works. Okay. Now, this is quantum reality. Now, it's curious, but as far as I can make out, they both make a consistent picture. Now, I have here a pretty severe test for the picture. This is an example of an Einstein, Podoski, Rosen situation. Time is going up the picture as before, and you might slice it in different ways, have different observers looking at the situation. But the real observers in the picture here are Alice and Bob, for some reason. Well, they're A and B, I suppose. So Alice and Bob are considered to be these two observers. They each take away from the initial state. Imagine their states are represented by the black lines going up. Alice goes up to the left, and Bob is up to the right. They start off together, and each of them they're presented with a box which contains a particle of spin 0, so it has no direction attached to it. Then this is split into two spin half particles, and Alice is given one of them in this closed box. Bob is given the other one, and they go away to a long distance apart, maybe light years apart, even if you like, or they could be different planets, a long way away. And then they settle down. And so that's the picture. You can see them separating, and then they settle down. And then one of them, let's say Alice, has a look and makes a measurement in a certain direction. In this case, the measurement direction, I think, is up and to the right. You can see that little arrow. Her measurement is the top point on Alice's line, and she's making the measurement, and she finds the answer, no, it's not that direction, it's the other way. Now, Bob, later on, and his measurement point is somewhere further up on his line. And he makes a measurement, and there are certain rules which prevent Alice from sending signals faster than light. The crucial thing about this is that you can't send signals faster than light. And does it make sense? Well, it does. But what is the quantum reality? It's very strange. The quantum reality, as you can fiddle around and see what it must be by looking at observers moving with different speeds and so on, must travel back on the past cone. So it looks sort of retroactive. Alice has made her measurement, and she's seen that it's not in the direction she chose, which was up to the right. It's therefore turns out to be the opposite direction, because that's the only possibility, is yes or no on a spin half particle. Either yes or no, it says, nope, you got it wrong. And so this information travels backwards along the past light cone. So you see these sloping lines away from her point, right on the top point on the left-hand branch. the sloping lines are the path light cone of Alice's path light cone. And when it hits Bob's world line, that is the quantum reality of his particle. So the quantum reality has become the opposite of what Alice's one is. But since Bob can't say, hello, state, what is your state? That's not allowed. It's only quantum reality. All he can do is try different possibilities and see what the answer is. Very strange picture, but it does seem to be completely consistent. So the quantum reality goes backwards in time. Bob makes a measurement. He can't use this information to send a signal faster than light because that's not the way quantum reality works. The way quantum reality works is that if he had chosen the right answer, which would have been opposite to Alice's, well, I guess the same direction as Alice, then he would have got the answer, yes, you got it right. But he has no way of telling that without Alice sending a signal to him, and that would be slower than the speed of light, and so she can't do that. So although the quantum reality has become a kind of reality for Bob, it's not something that he can do anything with apart from you make a probabilistic measurement. And then he makes it later on, and then his quantum reality goes back and hits Alice's world line before she's made her measurement. So when you know the full answer in the picture, sort of godlike, you look at the whole picture and you see what the results were they made. You can then work out what the quantum reality must have been. But there was no way that either one of them could have determined what this quantum reality is. So it seems to be a consistent picture, a peculiar one, but nevertheless, that's the picture. Okay, now in this picture, I have a sort of combination of quantum and classical reality in the sort of way I understand it. At the bottom, I imagine a laser which is sending a high-energy photon to a beam splitter, or half-silvered mirror, if you like. So this photon is split into going horizontally and going vertically. Vertically downwards, so you won't worry about it, it just goes down. If it goes vertically or horizontally, then it hits this lump of material, and considering it's a pretty energetic photon, so it hits it and starts to move it. But since the photon is in a superposition of being horizontal and going down, the impact on this body will be a superposition. Now, as you move your way up the picture, and you can see the classical reality is determined by the curvature of the space-time is produced by that body as it's put into a superposition of two locations. And this goes up until the Dioschi time, if you like, is when the collapse is supposed to take place. And if you like, that's sort of where consciousness comes into the picture. It retroactively, since it went the other way in this picture, it retroactively goes back to the classical reality is what the classical space-time does, and you have to say, well, the classical reality of that space-time goes right back to where the thing started to bifurcate. And so the classical reality you see with this marked at the left-hand side upper part of the picture, and the quantum reality sort of encompasses both until the collapse takes place. And somehow the quantum experience has to do with the branching of the two. Now, there's always been a problem, I think, as Stuart emphasized in his talk, about things seeming to happen too fast. And I here have a picture, rather crudely drawn, of somebody playing tennis and has deciding at the last minute whether to hit it right or left. And according to conventional neurophysiology, it's too late to make a conscious decision because it has to be done much too fast for the nerve signals to take place. Nevertheless, the conscious Roger Federer or somebody down there who's decided to hit the ball one way or the other, and that choice, according to him, was made consciously. Now, according to conventional neurophysiology, that can't be because there isn't time. But I'm trying to argue that no, that consciousness could be, as long as it has this retroactive aspect. It somehow feels out what's happening in the future and retroactively goes back. So it's got to be as though somehow the two alternatives of going one way or the other are coded already in some kind of superposition. At what level and where, I'll leave it to Stuart to make a comment about that. But somehow these two alternatives are there, programmed in a certain sense in quantum superposition. And the choice can be made in this retroactive way to influence which choice actually is the one that's made. So that it could be a conscious decision, although it can't be understood in these terms. Now, this all ties in with these early, very remarkable experiments done by Benjamin Libet, which I did talk about in my book, The Emperor's New Mind, right at the end, and I gave a sort of explanation which is the one which I would believe now, strangely enough, although I didn't explore it at that time. What is this experiment? Well, you have somebody with an operation on the brain, which has nothing to do with the experiment. The experimenter was given permission to do this experiment while the patient had a brain revealed, I guess, and electrodes on the finger and the corresponding another electrode on that part of the sensory cortex, which will tell you where the feeling of the sensation will be registered in the brain. So you see this little mark at the top. I'm going to work my way down the picture. This little mark at the top is the stimulation of the finger. And you ask the patient, well, when did that happen? And there's a fast-moving clock on the wall. And the patient says it was at such and such a time, which is almost coincident with the actual time. And so the feeling of the stimulation of the finger is indicated just below the mark there. Now going to the second horizontal picture, and now we have a brain stimulation, and curiously enough, at up to half a second, nothing is felt. The bottom picture shows you more what happens. Up to about half a second, nothing is felt, and then after half a second, then it is felt. The brain stimulation is felt as though the finger had been stimulated, but not the same. The patient can distinguish the actual stimulation of the finger from the brain stimulation. But it does feel sort of as though the finger has been stimulated. It takes half a second, that long. Now, this is the very remarkable one. The next line, suppose the finger is first stimulated, then a quarter of a second later, the part of the brain is stimulated, and somehow nothing is felt about the actual stimulation of the finger. It's only the brain stimulation is felt half a second after that starts. Somehow, the feeling of the stimulation of the finger it's unfelt. And that's a real paradox, unless somehow the feeling is not actually felt until later, and then about the clock isn't seen, sort of registers as being later. So that's consistent with the top line. So both things do not happen until later, but somehow it's referred back as though it had been earlier. And so in the bottom line, you can see that if the brain stimulation is first, then it sort of makes sense again. I won't go into the details of that, but it does seem to me it would be very nice to have this experiment repeated. And I don't know, Stuart will explain why it hasn't been done again. I think it really important experiment that should be done. Some version of this experiment should be done again. And this wasn't before, it was still in the 1990s, I think, when this was done originally. I'm going to end with what I'm calling is the Hemingway paradox. Quite curious, because poor old Ernest Hemingway apparently committed suicide by aiming a gun at himself and pulling the trigger. Now, why I'm calling it the Hemingway paradox, because by the time he pulled the trigger, he was dead, and so how could he decide to pull the trigger? Because that would have been later than pulling the trigger. And I must say, I was quite worried by this, because it seems that how could he later have decided to pull the trigger and then retroactively pulled it when he was already dead by then? Well, what's the answer? The answer, in my view, is that's because the quantum reality does exist, and it persists in a certain sense. And so his experience or his decision to pull the trigger was in the quantum reality. That got wiped out later because the classical reality becomes the firmer reality, which is the thing which persists. But nevertheless, his decision to pull the trigger actually occurred, according to this viewpoint, in the quantum reality, which could have occurred a quarter of a second later, and he pulled the trigger. Sad story, but nevertheless, that's the view I'm taking. Thank you very much.